So in this problem, it says that we have a 0.5 meter cubed rigid tank that contains refrigerant 134A initially at 200 kilopascals and 40% quality. And then it says heat is transferred to the refrigerant from a source at 35 degrees Celsius until the pressure rises to 400 kilopascal. Determine A, the entropy change of the refrigerant, B, the entropy change of the heat source, and C, the total entropy change for this process. So this problem is actually, it's pretty much like problems we have been doing for closed systems, but now we're taking it a step further and we're saying, does this process meet the second law requirement? So a big part of this problem is stuff that we've already done before. Now we're just going to take it a step further and do some calculations for the entropy as well. So let's go ahead and set up our problem. So I always do these problems the same. So I always start with a problem setup, and that's usually just a drawing of the problem, like nothing fancy, just a really basic drawing. I write down all of the information that I was given in the problem and then the information that I'm looking for. So first of all, this says that we have a tank. So it's basically a closed system. So and we have refrigerant inside this tank. We know that that heat is being transferred in. So heat is being transferred in, so Q in, and then it tells us that our source, so I'm just going to say that's the temperature of the surroundings, is 35 degrees Celsius. All right, so now let's write down some other information from this problem. So first of all, since this is a rigid sealed tank, we know that V1 is equal to V2, which means that the specific volumes also have to be equal. And it tells us the size. So it says that V is 0.5 meters cubed. And then it also gives us the initial pressure. So we know that P1 is 200 kilopascals, and gives us the quality, so we know that X is 0.4, and so then since we're given a quality, we know that this is a saturated mixture, so that means that at least for the initial state, we have everything we need to look up our data on the tables. And then it tells us the pressure rises to 400 kilopascals, so we know that P2 is 400 kilopascals, and it's asking us to find the change in entropy of the system, the change in entropy of the surroundings, and the total change in entropy. So this is basically all of the information that we have from the problem. Let's also make some assumptions, just so we kind of know what we're working with. First of all, this tank is stationary and it's not huge, so 0.5 meters cubed. It's not like meters tall, so we probably don't need to take into account change in potential energy. Since it's stationary, we're going to say the change in kinetic energy is 0, change in potential energy is 0. So that just means we don't need to consider those terms in our energy balance. And then there's also no work. So this is it says that there's heat being transferred in, but there's no, it doesn't say anything about a paddle wheel or there's no moving boundaries, so we don't have boundary work. There's no electrical work, at least not that it's told us about, so we can assume that the work is 0. So let's go ahead and write our equations. So first of all, we're looking for the change in entropy of the system and the change in entropy of the surroundings. And then we know that the total change in entropy is just those added together. So let's start with the change in entropy of the system. This is just equal to the mass multiplied by S2 minus S1. And we're going to get these from the table. So the reason why we're multiplying this by the mass is because the entropy data on the table is on a per mass basis. And we can also calculate the mass because we know the volume and we can look up the specific volume on the table. So we're going to calculate, so mass is equal to V over the specific volume, and we're going to get this from table. All right, so we have everything for that. I'm just going to specify table for those. So we're just going to look those up. Now for the change in entropy of the surrounding, this is equal to Q over T. And the reason why we can use this form of the equation is because we've assumed that T is constant, so we've assumed that our source, which is the surroundings, we've assumed that that's isothermal. So basically we can take the temperature out of the integration, and so then when we integrate we get this form of the equation. So just keep that in mind. If you have a temperature source that's not isothermal, you're not going to be able to use this equation. So we're going to get Q from the first law. So we're just going to solve the first law energy balance to get Q. And then T is known, so it was given. So let's write down the equation for first law energy balance. So we have Q minus W is equal to delta U plus delta KE plus delta PE. So we've already assumed that these two terms are zero, and we've assumed that the work is zero. So then Q is just equal to the mass multiplied by U2 minus U1. And we're going to look these up on the tables. That looks like pretty much all of the equations that we're going to need. The next step is to look up the data. So let's do that. So data. And when you're doing these problems, I always recommend do them in a really ordered fashion like what I'm doing. If you try to mix things together or skip parts, that's where these problems can get really confusing. So I think the confusion with these problems is usually not so much that the problem is hard, it's just that these problems are long, they have a lot of steps, and so you just want to kind of be really, like, just approach the problems in a really ordered way, and you're always going to be able to do them correctly. All right, so I like to write down the information for each state that I'm actually looking up the data for, just so it's really clear. So for state 1, it gave us the P2 was 200 kilopascals, X was 0.4. We knew this was a saturated mixture. So, and we know that, so S1 is equal to, and since entropy is a property, we can use this equation with the quality to calculate what it is. So SF plus X SFG, and then we're going to get SF and SFG off the table. So this is equal to 0.468 kilojoules kilogram Kelvin. And then we're going to do the same thing. So we also need U1. So this is UF plus X UFG. This is equal to 112.8 kilojoules per kilogram. And then V1 is equal to VF plus X VFG. And this is equal to 0.0404 meters cubed per kilogram. And I didn't put in numbers, but I recommend that you actually go look these up and verify that these are the numbers that you get. I didn't write down all the numbers just to save time, but I just got SF and SFG and UFG off the table. So for instance, SF, if you look it up at 200 kilopascals for a saturated mixture, you get that it's 0.15449 kilojoules, kilogram, Kelvin, and then so on for all of them. So I recommend looking those up and just verify that you're getting the same numbers. And then for state 2, we have the P2 is equal to 400 kilopascals, and then we know that V2 is equal to V1, and we have that, so that's equal to 0.0404 meters cubed per kilogram. And we're not sure of the phase, so we need to figure that out. So what we're going to do is look up VF and VG at this pressure. So VF is 0.000795 meters cubed per kilogram, and VG is 0.051266 meters cubed per kilogram. So then we can just look at where V2 falls within these. So V2 is greater than VF, but it's less than VG, which means that we have a saturated mixture. So that adds not a huge complication, but just makes it a little bit longer to find our properties because we need to calculate what the quality is first. So we can calculate the quality with this. So we know that V2 is equal to VF plus X VFG, which we've already looked those up. And so then we have 0.0404 meters cubed per kilogram is equal to VF as 0.00777905 meters cubed per kilogram plus X, which is what we're looking for. And then this is 0.051266 minus 0.0007905 because it's VFG. And so then X is equal to 0.77. All right, so now that we know the quality, we can find, and we know the pressure, and we know that this is a saturated mixture, and we know we can use that data. So we have everything we need to look up our data for state 2. So what we're finding is the entropy at state 2, so this is equal to SF plus X SFG, and U2 is equal to UF plus X UFG. And so then what we're going to do is the same thing we did before, just look up these values on the table, and then we can solve. We know the quality now, so then we can solve these equations for the entropy and the internal energy at state 2. And so just as an example, SF is equal to 0.24757 kilojoules, kilogram, Kelvin. So I'm not going to go through and write all of these down, but I recommend that you look them up and verify that you're getting the same numbers I am. And if you get different numbers and you're sure that you're right, then there's a chance I could be wrong. So anyway. So what I got was that S2 is equal to 0.7708 kilojoules, kilogram, Kelvin, and U2 is equal to 195.66 kilojoules per kilogram. So now we have all of our data, and we're pretty much ready to just solve equations. So let's solve. So notice how before jumping to solving anything, I've written down all of the information from the problem. I've written down assumptions. I've written down equations we're using. I've looked up all of the data. So really, at this point, it's a matter of just plugging numbers into the equations. This is how you want to do it. Like, you don't want to try and solve equations before you've gone through all of this process, because if you start with an equation and you just start trying to plug numbers in and see if it matches the answer in the book or online, you might get the right answer, but it's not gonna be really clear why, and you probably won't get the right answer. So with these problems and with any engineering class, like pretty much from this class on, we're going to be doing fluids, heat transfer, mass transfer, all of those classes where you're doing these balances and using these equations. You want to approach all of these problems in the same way. Like, you want to be really ordered about how you set them up and how you solve them. It's going to save you a ton of time. All right, so let's solve our equations. And I'm just going to write down the equation just so it's here. These are the equations that we wrote down earlier. So and we needed the mass, so that's just mass over the volume that was given divided by the specific volume. So this was 0.5 meters cubed divided by 0.0404 meters cubed per kilogram. So then the meters cubed cancel and we're left with kilogram. This works out to 12.4 kilogram. And then the change in entropy of the system is equal to 12.4 kilogram multiplied by, and then we just put in S2 and S1 that we got from the tables. So 0.7708 kilojoules kilogram Kelvin minus 0.468 kilojoules kilogram Kelvin, and this is equal to plus 3.8 kilojoules per kilogram. All right, now let's do the change in entropy for the surroundings. So change in entropy for the surroundings is equal to Q over T. And remember, we're using this equation because we assumed that our source is isothermal. In other words, it's not changing temperature. And we needed to calculate Q. So we got Q from the first law energy balance, so U2 minus U1, so is equal to 12.4 kilograms. And this is just a matter of plugging in the data that we got from the tables. So 195.66 kilojoules per kilogram minus 112.8 kilojoules per kilogram. And this is equal to 1028 kilojoules. So then Q in is equal to 1028 kilojoules. And it's positive because the heat is in. We need to think about this for a second. So we're calculating the heat. So we're calculating the change in entropy from the surroundings. So we have our system and we have the surroundings, and the heat's doing this. So it's going into the system, it's going out of the surroundings. So that means that Q from the surroundings is negative 1028 kilojoules. So make sure to think about the signs when you're doing this. All right, so then delta S surroundings is equal to minus 1028 kilojoules over 307 Kelvin, because we converted Celsius to Kelvin. And this is negative 3.35 kilojoules per kilogram. And remember that we can have, like, this can be negative. Like, we can have a negative change in entropy. It's just that the total entropy for both the system and the surroundings has to be greater than 1. So now what we're going to do is calculate the total entropy. So this is just equal to the system plus the surroundings, which is equal to 3.8 kilojoules per kilogram, plus, and then this is negative 3.35 kilojoules per kilogram. So then this works out to 0.45 kilojoules per Kelvin. And these aren't per kilogram, these are per Kelvin. Just get used to kilojoules per kilogram. All right, so kilojoules per Kelvin. All right, so since this is positive, so the total entropy is positive, this satisfies the second law.